Okay, so let's look at carbon and hydrogen. So here we have carbon. Carbon has 4 valence electrons, and so they'll be arranged like this, and here's hydrogen. And so we can imagine one hydrogen atom overlapping with one of those. There's another hydrogen atom that's going to overlap with this one. And so we can envision something like this. Here's one half-filled p orbital on carbon, and here's a second half-filled p orbital on carbon. There's carbon's s orbital. And so the hydrogen with its 1 electron overlaps with carbon's orbital, and so we get a pair of electrons here. And that pair of electrons, that overlap of orbitals, is the bond. And the other p orbital is perpendicular to that, and so we'll get another one down here. So here, what we're talking about is predicting a bond angle of 90 degrees and a chemical formula of CH2. Because we look at this and it's like, well, 2 hydrogens and 1 carbon, and that's all that can happen. But the reality is that it's actually CH4, and the bond angles are 109.5, not 90 degrees. So something's missing from this idea. So far, we've been assuming that when the orbitals overlap in a molecule, that they remain the same, they remain unchanged, and that's not the case. And so hybridization is the missing concept. So hybridization is a mathematical procedure in which we take those standard atomic orbitals and combine them to form hybrid orbitals. You can think of hybridization as being sort of like an averaging. We're going to combine these orbitals and average them, and then we're going to end up with new orbitals. This gives us a much better prediction of what actually happens. We're still looking at these orbitals as being localized on atoms, but now the shapes and energies are going to be different than the regular orbitals. The hybrid orbitals are going to minimize the energy of a molecule by maximizing the overlap. More overlap is better because you get more of the electron density between the atoms, and you get a better attraction between the 2 atoms. So we're going to focus on hybridization of only the interior atoms and assume that the terminal atoms are unhybridized. So this is a simplification, but it works well enough for our purposes. So some things we have to remember. The number of standard orbitals is always equal to the number of hybrid orbitals. So you could say this is the law of orbital conservation. If you start with 2 orbitals and you hybridize them, you end up with 2 hybrid orbitals. The shapes and energies of the hybrids are going to depend on the shapes and energies of the regular orbitals that you're hybridizing. The particular type of hybridization is whatever's going to give the lowest overall energy. This can be calculated, but it's way beyond the scope of this class. And so we're going to cheat a little, and we're going to use VSEPR theory to predict what the hybridization is. So we're going to look at what happens in CH4 methane. So here we have an orbital diagram for carbon. So there's a 2s orbital that has 2 electrons in it, and we have 3 p orbitals here, the 2 p orbitals, and they'll each have 1 electron. We can take these 4 orbitals and hybridize them, blend them up, average them, and we end up with 4 new orbitals. These orbitals were 2 different kinds, and they had different energies. When we hybridize them, now they all have the same energy. And this energy is less than the energy of the p orbital, but more than the energy of the s orbital. Because these are all the same energy, we call that degenerate. And so we name these sp3 because we took 1 s and 3 p orbitals and smushed them together. So sp1, 2, 3, sp3. Any questions? So what would this look like? So here we have representations of s and p orbitals, and we looked at these shapes earlier. And so when we take these four shapes and combine them mathematically, we end up with four new shapes. And it's a little hard to imagine how that works out, but just go with it. So each of these new orbitals has the same shape, has the same energy, but they're going to be oriented in space to get away from each other, just like in Vesper theory. So these, instead of the p orbitals where they're oriented along x, y, and z planes or lines, axes, these are four that need to get away from each other, and so in three-dimensional space they will make a tetrahedron. When we look at all of them put together, these have lobes, two lobes, kind of like the p orbitals do, but one lobe is much larger and one is much smaller. The smaller one is not as important, and so when we draw them all together, we leave the smallest lobe out because the drawing would get super messy and confusing. So we just leave it out. But it's there, we understand that it's still there. But so our new hybrid orbitals are going to be oriented like this in a tetrahedron. So we can draw a new orbital diagram, and now we have four boxes that are together because they're all the same energy, and now carbon's 4 electrons will follow Hund's rule and fill those individually, and so we'll end up with 4 half-filled orbitals. Each of these orbitals can overlap with the s orbital of one hydrogen atom. Oops. So these guys can overlap. These guys can overlap. And this could overlap, and this could overlap. You get the idea? So here we have those 4 hybrid orbitals. I think this is kind of cool because the author uses blue for s orbitals and red for p orbitals. And what happens when you mix blue and red? You get purple, right? So the hybrid orbitals are purple. So here we have the hybrid orbitals of carbon. They each have 1 electron, and each of those can overlap with the s orbital of a hydrogen atom, and that's going to form a bond. This is going to predict that this molecule is tetrahedral, which is what we observe experimentally, and that the formula will be CH4. Any questions? What about lone pairs? Well, we can have lone pairs in hybrid orbitals. So here's ammonia. Nitrogen has a lone pair, and so it's going to half fill. Actually, let's do this. So here's the sp3 hybrid orbitals for nitrogen. And we know from looking at the periodic table, nitrogen has 5 valence electrons. And so they'll go in like this: 1, 2, 3, 4. And then the 5th one has to pair up. So this is a lone pair. That's this guy up here. And then we have 3 half-filled orbitals. And each of those, these 3 guys here, can overlap with hydrogen and form a bond. In Vesper theory, we talked about how the lone pair was more repulsive and pushes these guys a little bit closer together. In valence bond theory, the presence of that lone pair reduces the tendency to hybridize, and so these hybrid orbitals are going to have a slightly different shape, and was like, okay, they've got it covered, I'm not going to worry about it. So how many hybrid or sp3 hybrid orbitals result from the hybridization of one s and 3 p orbitals? I'll find my chat window. Anybody? What's 1 plus 3? 4. Thank you. 4. So we hybridize 1 s and 3 p, we get 4. Well, what if we don't use all of those? What if we just use 2 of the p orbitals and an s orbital? Then the combination of these 3 orbitals will give us 3 hybrid orbitals, and here we're going to call these sp2 because there's 1 s and 2 of the p orbitals put together, so sp2. These are going to have the same energy as each other, and that will be between the energy of the p and the s orbitals. The unhybridized p orbital is just going to sit out here exactly like it was before, just left over. When we do this 1s and 2 p's, we get these lobed shapes again with 1 small lobe and 1 large lobe. And the shape and size is not exactly the same, but it's similar to an sp3. But they're oriented in space 3 things to get away from each other, and so they're going to make a triangle, a trigonal planar arrangement. The sp2 hybridization enables the forming of double bonds. And so here we're going to look at H2CO. This has sp2 hybrid orbitals. So the carbon, here's its unhybridized orbital diagram, and here's the hybridized orbital diagram. So it's going to put these 3 together and hybridize them, and this one's going to remain unhybridized. So there's the unhybridized. Now you might ask, well, why is this electron over here? Shouldn't it be paired up in here? Well, these are now closer in energy than the original s and p orbitals, and so it's worth the extra energy for this guy to have his own orbital, and so it will put an electron in there. So here we have carbon with its that's carbon with its regular orbitals. Here's oxygen and here's hydrogen. So I think what I'm going to do, I'm going to mess with this a little bit. Because I want to be able to look at the two oxygens with the carbon. So here I have 2 oxygens. Oops, another electron in there. Each of them have 2 half-filled p orbitals, and I have this hydrogen. So the hydrogen can overlap with one of the hybrid orbitals, and this half-filled orbital from oxygen can overlap with 1, and this half-filled orbital can overlap with 1. And then oh, I know what the problem is. It's 2 hydrogens. Duh. It's like, wait a minute, this isn't working. I need 2 hydrogens. It's not H2. It's H2, not O2. Okay, let's try that again. We're going to ignore this one because we're going to use the hybridized orbitals. Okay, so hydrogen overlaps with one of these half-filled orbitals. The other hydrogen overlaps with one of the half-filled orbitals. This is in my way, so I'm going to make it go away. One of these half-filled orbitals overlaps with that. And so those are going to make a trigonal planar shape. And then I've got a p orbital on oxygen and an unhybridized p orbital on the carbon, and those are going to overlap. So let's see what that looks like. Looks like we're turning into balloon artists or something, right? Here's our carbon. It has sp2 hybridized orbitals, so those are 3 equivalent orbitals, and they're going to arrange themselves in a triangle. One of those can overlap with hydrogen, another one can overlap with another hydrogen, and the third one will overlap with that half-filled p orbital on oxygen. That leaves an unhybridized p orbital on the carbon and a regular p orbital on the oxygen. Now, when these overlap, because they are parallel to each other and separated by a distance, they overlap side to side instead of end to end. So the end-to-end overlap is called a sigma bond, and this side-to-side overlap is called a pi bond. And if you look at it from the side, it kind of looks like the letter pi, right? Sigma looks a lot like an O, and if we look down this axis from the oxygen to the carbon, this bond would be symmetrical. We would just see a sphere, right? Whereas looking at this one, we've got these 2 pieces. So this is the double bond. A sigma bond between a hybrid orbital and one of oxygen's orbitals, and then an unhybridized p orbital overlapping with oxygen. And it's important to understand that this all is one orbital with one pair of electrons. And how can a pair of electrons both be in both places at once? Well, that's the wave-particle duality of electrons. It's like a standing wave. It can be in 2 places at once. Any questions? So pi bond is when we have the side-to-side overlap like this. We can also have unhybridized p orbitals that overlap end-to-end, and that forms a sigma bond. So pi bond is side-to-side overlap of p orbitals. The electrons occupy both lobes. So this pair of electrons is up here and down here, just like the one electron in this is here and here at the same time. Here they overlap end to end. That's a sigma bond. So we can label these bonds, and you're going to use this notation on the worksheet. And the way we label these is first we use either pi or sigma to describe what type of bond. So here we have a side-to-side overlap, and so this is a pi bond. Then there's a colon, and then we're going to list the 2 elements that are in this bond. So we've got carbon and oxygen. The order doesn't really matter. And we're using a p orbital on this carbon and a p orbital on the oxygen. And so this is the description for this pi bond. This bond in the middle here is a sigma bond, end-to-end overlapping, like, like this, overlapping like this. So that's called sigma with a colon, and then we're specifying the two elements, carbon and oxygen, and then we're indicating what kind of orbitals are involved. Well, on the carbon, we're using one of those hybrid orbitals, sp2, and the oxygen is using a p orbital. So that's that one. And then we have two bonds over here. They are the same kind of bond, and so they'll have the same description. Sigma CsP2 HS. The hydrogen is using an s orbital, the carbon is using an sp2 orbital. Any questions? This is like the foundation of it. We get a lot more insight into the molecule and the bonds using valence bond theory. We understand now that the double bond that we see between carbon and oxygen is not two identical bonds. It's actually two different kinds of bonds. One is stronger than the other, and we observe this experimentally, that the pi bond is easier to break than the sigma bond. The overlap is not as good. So anytime in the Lewis model that we see a double bond, we need to understand that it always corresponds to a sigma and pi bond in the valence bond theory. This also helps us to understand rotation of molecules. So in this molecule, there is a single bond between the two carbon atoms, and that's going to be a sigma bond. Single bonds are always sigma bonds, single sigma. So the first bond that forms is always a sigma bond. This is symmetrical, and so we can rotate each end of this. It's a little bit like when you stick your fingers together and you can rotate your hand, right? So these can swing around and rotate. Here we've got a double bond. The double bond is the sigma bond plus a pi bond. And now, like, if you put two fingers together, I can't rotate my hand without breaking the bond, right? It doesn't go anymore. So there's no rotation here. And we observe that experimentally because there are two different kinds of molecules from that compound. So this is the same two compounds. Here's with the single bond, we've got free rotation. These are the space-filling models. And here's the double bond. The double bond, these can't rotate, and so we get two distinct forms. One where the chlorines are on the same side of the carbon bond, and one where the chlorines are on the opposite side. And this molecule cannot transform into that molecule without the breaking of bonds. Here we can go from this one to that one just by rotation. And so these are actually two distinct compounds. They have slightly different properties and they have different names. This one's called cis because these are on the same side, and this is trans because they are across. So we can also take an s orbital and one p orbital, and that would make an sp hybrid orbitals. And then that leaves these two unchanged orbitals out here, and this is going to allow the possibility of a triple bond. So when we take these two and combine them, we end up with two orbitals, and they orient like we learned in Vesper theory, opposite sides, and so this is a linear geometry. It's important to understand that this, although it looks like the same shape as this red one over here, this is actually two sp orbitals because we are not showing, maybe white would be better. we are not showing the small lobes because it gets really messy. But this has a large lobe and a small lobe. This one has a large lobe and a small lobe. So if we look at acetylene, here we have 2 carbons and 2 hydrogens, and there's a triple bond with the carbon. So the carbon is going to undergo sp hybridization. It's going to make 2 sp orbitals, and then it'll leave 2 p orbitals. And so if we look at how does this happen, let's draw the rest of this in here. Okay, so, oh, shoot. Seriously? Okay, hang on a minute here. Probably be faster at this point to just draw it over again. Okay, fine, whatever. That's just really unfortunate. So this is my hydrogen, sp, and regular p orbitals. Try not to push the wrong button this time. So we've got a lot of half-filled orbitals here. So the sp orbital of one carbon can overlap and form a sigma bond with an sp orbital of the other carbon. This is the other carbon. And this sp orbital will overlap with the hydrogen and form a sigma bond. And this will overlap over here and form a sigma bond. And then we've got these half-filled unhybridized p orbitals. And so those are going to overlap with each other in a side-to-side way and make pi bonds. I don't know if that mess helps or not, but there it is. So it looks like this. So this carbon has sp hybridization, so it's got these 2 sp hybrid orbitals. One overlaps with hydrogen, one overlaps with the sp hybrid of the other carbon. Then it's got 2 unhybridized p orbitals, one in the horizontal position here and one vertical. The other carbon also has vertical and horizontal p orbitals, and so those are going to overlap side to side. And so we've got one pi bond here and another pi bond up here. And so the sigma orbital and 2 pi, sigma bond and 2 pi bonds gives us that triple bond. Any questions? So this one might be worth looking at. What's the hybridization of carbon and CO2? we have to look at the Lewis structure. So carbon here is making 2 double bonds. Each of these double bonds has a sigma bond and a pi bond. There's a sigma bond and a pi bond, a sigma bond and a pi bond. So if carbon is going to make 2 sigma bonds, how many hybrid orbitals does it need? Nice kitty. To make 2 sigma bonds, it needs 2 orbitals. And so it's going to, from its original S and 3 P's, we're going to get SP, and we're going to leave 2 P's alone. So these are the hybrid orbitals that are going to form the sigma bonds, and these unhybridized p orbitals are going to form the pi bonds. So this is going to form sp hybridization. So in the Lewis theory, we talked about how we can have expanded octets. And what happens in valence bond theory is now we're expanding into the d orbitals. The energy of the 3d orbitals is similar to the energy of the 3s and the 3p. And so this sort of thing can happen. So here we've got an s orbital and 3 of the p orbitals and 1 of the d orbitals. And so this is called sp3d. And one of the videos that I kind of like, they call this dsp3. So don't let that bother you. The thing to understand here is that these are not 4d orbitals, they are 3d orbitals. They're in the same principal energy level. So if we think about the quantum hotel, there's the 3rd floor, the 2nd floor, and the 1st floor. We've got S, P, and D rooms. For something like sulfur or phosphorus, these lower orbitals are going to be full, but those aren't the ones we're interested in. It's the valence electrons that we're interested in. So let's maybe use sulfur as an example. I should have drawn that in black. Sulfur has 1, 2, 3, 4, 5. Let's use phosphorus. Phosphorus has 5. So it's S2P3 for its valence electrons. What happens here when we hybridize and bring in a d electron, is that we're going to move over into this empty d shell. So on the fourth floor, on the 4th principal energy level, there's also S, P, and D. And if we fill up 3s and 3p, we would next go to 4s before we fill up the 3d orbitals. But these 3d orbitals are there. And so all of this hybridization occurs within the same principal energy level. So in the hotel analogy, hybridization is like remodeling the floor, taking down some walls, maybe putting up some different walls. So if I'm going to form an sp3d hybrid orbital, I'm going to take the S room, the P room with its 3 beds, and part of the D room, and I'm going to make one large room out of them. And I took in five different beds, and so I'm still going to have 5 different beds. And I'm left with these d orbitals just sitting there. They were sitting there empty before, and they're still sitting there empty now. And there's a puppy. It's always fun to see the pets. So in the hotel analogy now, we've got 5 beds in the same room, and so they're at the same energy. There's the same cost to stay there. So now we have 5 sp3d hybrid orbitals, and then we've got these 4 unhybridized d orbitals that are still sitting there. Anybody have any questions about that? I think that's one of those things where you're like, I don't understand that enough to even have questions about it. It's okay. It's a lot to take in. But I just want to be very clear that the d orbitals here are the empty orbitals sitting right next to the s and p orbitals that we're having our valence electrons in. So we combine those and we get 1, 2, 3, 4, 5. Yeah, 5. Couldn't count there for a minute. Those all together will look like this. And just like 5 things in in Vesper theory made a trigonal bipyramid, these also make a trigonal bipyramid. So here's an example of that. We have arsenic trifluoride, pentafluoride. The arsenic needs 5 bonds with the fluorines, and so it will expand its octet. It will go into the d orbitals, and so we'll get sp3d hybridization, so 5 equivalent orbitals, and each of those can overlap with the p orbital from a fluorine atom. We can go a little further and take 2 of the d orbitals. We call this an sp3d2, and so there are 6, 1, 2, 3, 4, 5, 6, and they're going to arrange themselves like an octahedron. And sulfur hexafluoride is an example of this. So we have the 6 hybrid orbitals here, and each overlaps with 1 fluorine. So how do we know which hybridization scheme we should use on a given molecule? The rigorous method is you would calculate the degree and type of hybridization to give the lowest overall energy. That's way beyond the scope of this class. So we're going to go with good enough for Chem 1A. We're going to assign the hybridization scheme from the electron geometry of the interior atoms. Not 100% accurate, but good enough. So the idea there is we look at the Lewis diagram, and we look at the number of electron groups around the central atom, just like we did for Vesper theory, and we use the number of electron groups to tell us what the hybridization scheme should be. There's a table summarizing the different types of hybridization. And then here's directions for doing this. You start with the Lewis structure, use Vesper theory to predict the electron geometry, and then you select the correct hybridization. This is C table 10.3, but you don't really need to look at that table. you look at the number of electron groups, and that's how many orbitals need to hybridize. So if you have 2 electron groups, then you need to hybridize 2 orbitals, and that would be s and p. If you need 4 orbitals, because you have 4 electron groups, you'd use 4 sp3. You sketch the molecule, show the overlap, label the bonds. Thankfully for you, I'm not going to make you draw these things. I'm going to do this one. I'm not going to do all of these because you can go look at these in the regular videos. But let's just go through the steps here. So HCN, we have to start with the Lewis structure. We've got 1 electron for hydrogen and 4 for carbon and 5 for nitrogen, and so that's a total of 10 electrons. We've got 2, 4, 6, 8, 10. We're going to need some multiple bonds. So I'm going to move this electron pair in here to make a bond. Still don't have enough electrons, so I'm going to move 1 more. And I'm going to come up with that for my Lewis structure. I'm going to look at the central atom and ask myself, how many electron groups? Remember, a group can be a lone pair, a single bond, a double bond, or a triple bond. Each of those is just 1 group. So this has 2 groups, the single bond and the triple bond. So 2 groups means I'm going to use sp hybridization because I need 2 hybrid orbitals. So we can start here in the middle with the carbon atom, and the nitrogen's going to be over here, and the hydrogen's going to be over here. And I'll use the same colors. So the sp hybrids, the 2 of them are going to be 1 on each side. And the hydrogen has an s orbital, and so that's going to overlap. And so this overlap here is a sigma bond between hydrogen with an s orbital and carbon with an sp orbital. Over here we've got nitrogen. If we look at the orbital diagram for nitrogen, unhybridized, it has 3 half-filled p orbitals. So one of those half-filled p orbitals is going to be along the x-axis, and that's going to overlap end to end with my carbon hybrid orbital. So this describes this one. And this is going to be sigma carbon sp nitrogen p. The other orbitals that nitrogen has, wrong color, is a p orbital along the z-axis, the y-axis. Let's look here. So this is sp hybrid, and this is just the regular p. So carbon has 4 valence electrons, and so they're going to go like this. We've got 2 in the hybrid orbitals and 2 in the unhybridized orbitals. So this is one of our sp orbitals here, another one over here, and then carbon has 2 unhybridized p orbitals. So it has one in the along the y-axis, and so that's going to overlap side to side with that p orbital. And so we can label that one. That's a pi bond between a p orbital on the carbon and a p orbital on the nitrogen. So far everything's two-dimensional, not too bad, and here's where we get three-dimensional. So nitrogen also has, along the z-axis, a p orbital, and so does carbon. And so those can overlap side to side. I don't know if you can tell, but that's a slightly different red. The description for this bond is actually the same, because it's a pi bond between p orbital on carbon and a p orbital on nitrogen. And that's the hybridization bonding scheme for HCN. Any questions?